Nodal analysis is nothing special. You've already done it before. It's actually the same exact thing as doing KCL, but you are writing those currents in terms of V over R. So you're just using Ohm's law to write those currents. Over here is a little guide for you to look at if you want. So in this kind of scenario, you have two nodes, Vx and Vy, and you can write the current as just Vx minus Vy over R. If it was going upwards, for example, you would have Vy minus Vx over R. A little bit of a algorithm for how to do this is you identify your nodes of interest, you do KCL at those nodes, and then you solve for the node voltages by using either a matrix or by using substitution. So we start a little example over here on the bottom. Let's go ahead and look at our nodes first, so the nodes of interest. Here's our V2 node. Here's our V1 node. And here's going to be our 0 volt reference node, or our ground node, which is always needed in any kind of nodal analysis problem. So here's our 0 volt reference node. We could worry about this node over here, but that'll make our lives harder, and you'll see why in a few minutes. Okay, so because we're doing KCL at these nodes, we have to put in a direction for current, so let's go ahead and do that real quick. So let's choose the current going downwards over here, towards the right over here, and going down through the 6K, then towards the right over here. So following passive sign convention about the polarities, so here we go. Up, up, boop, boop, boop. So there we go. M plus minus, plus minus, plus minus. Okay, so we have all that settled. So let's go ahead and do KCL at the V2 node. So we'll say at V2. Okay, we have in is equal to out always. Okay, let's go ahead and do this. So only the 2 milliamps and this current over here is entering the V2 node. So this current over here is going to be V1 minus V2 over 6K. So the current over here, which is leaving the node, is going to be V2 minus 0 over 6K. Over here, we're going to write V2 minus 0 over 1K plus 2K. We could have written, V2 minus VO over 2K, but that would give us 3 unknowns, and that would be a lot to solve. Well, so what we can do instead is actually, have just 2 equations and 2 unknowns, solve for V2, and then use V2 to solve for VO via voltage division, which we'll go into in a few minutes. Right? So over here, what I'm doing is just saying that the 2K and 1K are in series, and so if we look at the voltage across them combined from here to here in the circuit, and then do that whole voltage or that whole resistance, that is the current through that branch. Okay, so for the V1 node, so at V1, set up. Here we have only the 12 milliamps entering the node. This current over here is going to be V1 minus 0 over 3K. We have the 2 milliamps from the source. This current over here is going to be V1 minus V2 over 6K. Okay, so just notice for a second how this current right here, this current was common in both equations. And notice how it didn't change. So over here is that current, and over here is that same current. It's always going to be V1 minus V2 over 6K. So depending on where we do KCL, that current will not change. It is defined in our case as V1 minus V2 over 6K. Alright, so basically at this point you could do some algebra and make your equations look a bit prettier, and then use substitution or like Cramer's rule, matrix to solve for V1 or V2. Now here they ask for V2 and VO, so we're going to solve for V2. So V2 is going to be 8.73 volts. So now we can use V2 to find VO because we have a known voltage here. The voltage across the 6K as just V2 minus 0, or just V2. So here, because we have a closed path in the circuit involving a known voltage and all series resistors in that closed path, we can use a voltage divider to solve for VO. So VO is going to be equal to V2 times 1K over 2K plus 1K. That is equal to 2.91 volts. Alright, and that is how you do nodal analysis. If this video helped you out in any kind of way, be sure to give it a thumbs up. See ya.